All right, guys, welcome back. We are going to continue our discussion of BGP. In this lesson here, we're going to focus primarily on just a couple of different attributes. We've gone through a couple of different discussions actually about the attributes and the best path selection process. And when we did our basic BGP operations and BGP overview, we talked a lot about the attributes. But today we're going to focus on traffic engineering with weight and local preference. This is our topology that we're using in this particular case. Probably will be the topology that we pretty much use for most of the rest of our BGP discussions. And I will save, since we're kind of making some changes here, I'll go ahead and save this topology or export this topology into the folder for traffic engineering with weight and local preference after the lesson's done. But that's basically what we're going to talk about today, specifically looking at the implementation of traffic engineering with BGP using these particular values, weight and local preference. Again, our goal here is to signal the outbound routing policy. All right. The key concept is that in this particular case, we're binding the BGP policy, we're applying that inbound. That's what's going to affect our outbound traffic flows. All right, so say we have two different connections to a different ISP. In this case, router 7 might be our service provider. We have a couple of ways to reach that service provider through R5. We have a couple of links that we can use, as well as going through R3. And we want to affect how the traffic leaves the network. These are going to be the two easiest attributes that we can apply to affect that policy decision, based on local preference and weight. Now, there's some significant differences between these two attributes. We need to understand what those differences are and how it's going to affect the scope of the IBGP domain with regard to a traffic selection process. Okay. Needless to say, these aren't the only attributes we can technically change. We actually have many other attributes we can change: origin code, next hop value, AS path. We could, for example, do some sort of AS path prepending, but normally we don't. We would select these two options because they're, quite frankly, the easiest options to implement. And depending on where they're implemented, they can provide a pretty basic understanding of, within the autonomous system, of how we choose to route. All right. Now, based on our previous discussion, let me go ahead and pull that up real quick. I want to just do a quick review of these two attributes, find out where they fall within the list, as well as what their basic function is. So weight, in the order of operations here, is the very first option that we're going to take a look at. It is a Cisco proprietary attribute. It gets applied as an inbound policy. It's assigned locally by the router. It's not propagated to the peers. It can have a value of anywhere from 0 to 65,535. The default weight is going to be applied to 32,768 for paths that I originate within the autonomous system, or a weight of 0 for all other prefixes. And in our particular case, the higher the number, the better. All right. And we're going to actually look at some examples of how we can apply this in our configuration as part of our demonstration process. The second option that we look at in this top-down processed list is local preference. This is a well-known discretionary attribute, so everybody that runs BGP understands what this attribute is. They can choose to ignore it, or they can choose to actually accept it, and then based on that make some sort of routing decision for a particular prefix. The default preference is 100. The higher the number, the better. And we set this with either, kind of globally with the BGP default local preference value, or we can actually manipulate this with route maps as well. We'll take a look at that application. All right. It's also not advertised to external peers. It's only advertised to internal peers. We're actually going to see as part of our discussion that the second option is typically going to be more preferred than the first option. And that's because weight is not an attribute that gets propagated to the rest of the peers. So it's very difficult to identified locally on a router. Let's say I've gone into my topology here and I've set the weight on router 4 to choose a path to router 5 versus a path to router 3. Remember, router 4 is our route reflector. Well, I don't see that weight attribute propagate to router 2 or router 1. So router 2 or router 1 may choose to use a next hop of 5.5.5.5 for those external prefixes, and we might think that's an error or that's some sort of incorrect routing decision based on our understanding of the entire topology, because we don't know how that routing decision was influenced. There's no weight attribute that we can see propagated from one peer to another. We could see the weight locally configured on router 4, but we wouldn't see it on any of the other routers. Whereas local preference is an attribute that is propagated to the peers. So if I go and look at my decisions, my routing decisions in the process, then that means that I'll see that on all of the routers themselves. Okay? All right? So we're going to take a look at this. It's typical that these attributes would be used for outbound path selection. Like I said, there's other options that we have. We do have other choices for deciding how to route out of our domain, but this is pretty much going to be the de facto standard. So let's take a look at how our network is set up. And let's specifically talk about some of these prefixes. In fact, I may end up wanting to add a few prefixes as part of this discussion. But let's just start with router 4, because router 4 is our route reflector in the iBGP domain. And I'm just going to do a quick show IP BGP and see if I see those external prefixes. I do. I see that the 8.8.8.8. I have 3 different ways of reaching that particular destination. The 75 subnet, I have a couple of different ways of reaching that prefix, that destination. 57, the 78 prefix. So we do have full convergence here. Now, whether or not we can actually reach those destinations is a completely different concept. So we'll talk about that as part of our discussion as we start to do our configurations. It's not really important in this particular case that we actually have packet reachability, with a ping or a trace route, because we can still analyze how BGP is making a decision even though we may not be able to route to those destinations. Remember, BGP is not a routing protocol. It is an application that allows us to identify network layer reachability information. All right? But it might be a good exercise to maybe troubleshoot, if we can't reach any destinations, troubleshoot some of those issues. Okay? So if I look at any prefix from router 4's perspective, we actually have a couple of different views. We take a look at the routers. We see how we're routing the traffic to get to a particular destination. And this is always going to be good practice in the lab exam as well, is to make sure that you just kind of familiarize yourself with what everything looks like specifically before you start making changes and going in and modifying the configuration per the instructions. All right. So I want to take a look into the decision process. Why did we choose one path over another path? So the first thing is, let's go ahead and start with the 78 subnet, because we do have 3 different ways of potentially reaching that 78 subnet. It does look like it's chosen a best path, and it looks like it's going to 37.7. But let's go ahead and do a ping to 172.16.78.8. Now, I don't expect that there would be reachability here. Remember, I'm on router 4. And I see a next hop attribute of 37.7. Do I have reachability to the 37 subnet? It looks like I do. So if I do a ping to 172.16.37.7, so it looks like there's something strange going on here. We got a couple of unique scenarios, right, where I can see that router 4 is making a decision as to what path to use. If I do a show IP route BGP, I can actually see those prefixes 57, 75, and 78 in the routing table. And if I look at the 37 subnet, that would be a little bit of a problem, wouldn't it? Because if you look here, 37.7 is the next hop, but I don't see 37 included in, as far as reachability goes, in my routing table. Let's see if we're getting that through some sort of IGP process. We might be getting that through an IGP process. And it looks like we are. Okay, so we're actually learning the 37 subnet through EIGRP. So it doesn't appear to be an issue on router 4 as far as reachability goes. And I suppose I would have to maybe do a couple of other tests, but most likely this ping, based on the next hop, is going to be sourced. Let's look back at the routing table again here. 37 is going to 34.3. So let's ping 172.16.34.3. All right, so I can definitely reach router 3. If I look at the destination, that's this link here. So most likely what's happening, in fact, let me go ahead and ping 172.16.37.3. Should be able to reach that. So it looks like it's probably going to be an issue on getting back to the other destinations. So if I do a show IP BGP, yeah, definitely. So we're seeing here that we're not really selecting, well, we've got a path for 1.1.1.1 that we've selected, 75.5. 75.5 is how we're getting to 4.4.4.4 and 3.3.3.3. So let's try this. Let me go back to router 4. Oops, I closed router 4. Get back into router 4 real quick. And let's do a ping to 172.16.37.7, and we're going to source that from loopback 0. Okay, so we do have reachability via the loopbacks. The loopbacks are included in BGP. So if we go ahead and source our traffic from the loopbacks, that's fine. We'll go ahead and assume that we're going to be sourcing our traffic from the loopbacks in this case. All right, so if I want to analyze the ultimate traffic flow, I go a trace route to 172.16.78.8, and I'm going to source that from loopback 0. We can see that we're taking a path through router 3 over the 37.7 link and then finally to 78.8. So we're going into AS51, AS51. All right. Now the question is, why am I choosing that particular path? And this is where it's really important. Depending on where you are in the BGP topology, who you're peering with within BGP, you may have a completely different view of the topology, and you might even be making a different decision. All right? And actually, it probably would make sense. Router 1 is probably ultimately going to make a different decision to get to the 78 subnet than, say, router 3 would. All right? But let's take a look. Let's go to router 4, and let's do a show IP BGP 172.16.78.0/24. And let's take a look at understanding how, what we call analyzing the traffic flow, understanding how router 4 is making this decision. We do eventually want the routers to agree how to reach a destination, but that doesn't necessarily mean that they're not going to take a different path. All right? Now, if I want to influence this decision process, I generally have two options: weight and local preference. Weight is a locally significant value, but remember, when you do your best path selection, you choose one as the best path. Any of the others that you did not choose are not ultimately going to get advertised as the best route. So now we have complete visibility because we are learning about these prefixes from different neighbors, different peers with different attributes. Now, router 4's view is going to be completely different than, say, router 1, router 2, or router 3, or even router 5. Because router 1, router 2, and router 3, and router 5 are route reflector clients of router 4. Router 4 is ultimately hiding the topology by making the decision on how to route on behalf of all the route reflector clients. All right. In this particular case, if I did affect weight, if I changed weight, because router 4 is a route reflector, this would probably be the optimal place to change the weight because it will affect how the other routers decide how to route. In other scenarios where we're maybe doing an IBGP full mesh and we're simply changing the weight, say on router 5 in this topology, if I were to change the weight on router 5 would not advertise both of these paths to router 4. It would only advertise the path that it chose, and ultimately router 4 would have to make a decision based on that. Okay? So in the case we saw router 4 is routing to router 3, going over the 37 link, going to router 7, and then using the 78.0 path to reach the 78.8. All right? So let's break it down, kind of identify how that's taking place based on what we see here. Okay, we see that we have 3 different paths available: received from a route reflector client from router 3, received from a route reflector client from router 5, and received from a route reflector client router 1. All right, if I go through the process of breaking down the decision, go through the decision tree, we start with weighting, and none of these particular prefixes are weighted. We don't see a weight value specified. We will after we make the change, but we don't see a weight value specified in this particular case. We then go to the local preference. Each one of these prefixes has a local preference of 100, okay, which means that that's a tie, and now we have to go to AS path. We see that the AS path length, in this case, that's all we're concerned with, is 1. So again, not really anything that we can make a decision based on. We look at the origin code next, and it shows incomplete in this case. That basically means that somebody did redistribution of this prefix into the BGP process. Actually, it's what I did on both of the external peers. I do a redistribute connected. All right. Let's see, what's after that? Look at the metric value. The metric value, which is the multi-exit discriminator, is all set to 0 for each of these prefixes. Keep in mind we're only going to look at the med by default when it comes from the same autonomous system. So that would be something like router 5 would choose to use the med and so on. Origin code is before AS path? No. If we look at the selection process here, we have local preference. This is not origin code. This is whether or not the route was locally originated, as opposed to a prefix I learned from another peer. Don't confuse locally originated with origin type or the origin code. All right? A lot of people get those confused. Locally originated is different than the origin type, origin, or what we refer to as the origin code. You see we've got internal versus a question mark, which is incomplete. Those are pretty much the only 2 codes you'll see. EBGP or EGP, excuse me, would not be something that you would see typically because we don't run EGP in our networks these days. Okay. So thank you for pointing that out, Ken. That's very important to understand, especially when you're kind of analyzing the paths. So if I was originating this path, which this is an external network coming from an eBGP peer, so there's no way it would be locally originated inside the autonomous system, I would choose that over any other option. But if, say, for example, I was looking at this from the perspective of router 8, that would be considered a locally originated route. In fact, let's go to router 8 and show IP route 170, router 8. Let me move this guy over here. There we go. Show IP route 172.16.78.0. All right. And we should see, well, it's connected. Show IP BGP 172.16.78.0/24. And what we should see here is, yeah, right here. So this is a local route. The quad 0 means it's locally originated, and we actually see the weight value applied here because locally originated routes always have a default weight of 32,768. Now it says the origin is incomplete, which is a little bit confusing, but if you look at show run pipe section BGP, we have to look at how this, we have to look at how this route is originated into BGP and is done through the process of redistribution, redistribute connected. So that's why it has an origin code of incomplete, but is still a locally originated route. Okay? All right. So we're back at router 4. We're still kind of going through the process of trying to discover how we ended up choosing a particular path. The MED is 0 for all 3 prefixes. That's where we left off. So now we're going to take a look at, is this an external path or is this an internal path? And we can see that all 3 of these are internal. All right. So now we're getting into the weeds a little bit because we're kind of like, okay, AS path didn't work, origin type, lowest multi-exit discriminator, and eBGP over iBGP, and then the lowest IGP metric. So this is actually, we got all the way down to step 8 when we decided to make our decision in this particular case, because we see the metric here is different than the metric here, which is different than the metric here. It actually wasn't a value that we were able to identify because we don't actually have that route in our routing process. So the metric, and this is what we're talking about, the IGP metric to reach the next hop, to reach 37.7 has a lower metric than to reach 57.7. So we ended up choosing that particular path because of the lowest metric. Okay. Now again, this doesn't have really anything to do with what we're talking about as far as manipulation, but it's important that you understand how this process works. Okay. So based on that, we know how the path is being selected. Now let's see if we can go ahead and influence this. Mike had a question, how is the metric different from the MED? The metric is reachability, defines reachability to the next hop using an IGP process. So if I do a show IP route EIGRP, I should see in this process here, to reach the 37 subnet has an EIGRP metric of 3072, which is reflected in this value here. So this indicates actually that recursion, that route recursion process that we use in BGP to actually recurse to the next hop. We're measuring the actual reachability through EIGRP to decide how we're going to choose that path. Sometimes that value is copied into the MED. I believe if I go over to router 7 and I do a show IP BGP, I should see, yeah, it's actually not copied by default. I was going to say I should see, let me do one more thing, show IP BGP 5.5.5.5/32. Yeah, it's not copied by default, but we can actually take that value and we can copy that value into the MED if we choose to, or we can just set the MED manually. So the MED is actually a BGP attribute, a well-known non-transitive discretionary attribute, whereas the metric itself is literally referencing the metric to reach the next hop. So again, looking at 57.7, I should see an EIGRP metric of 130816. Basically, the router is saying, you know what? It's going to be easier for me to reach. Did I cut it off? I must have cut it off. Let me do that again. Let's see, 57. How come I'm not seeing 57 in this case? That's interesting. I see 37. but I'm not seeing 57. Let me do a show IP EIGRP topology. Let's see. 37. 57 is not listed here. Let me take a look. So if I look at the BGP table, received from a route reflector client. Okay, so that's the client's metric to reach that particular destination. So I would have to go look at router 5 and do a show IP route EIGRP. And that should reflect in here. 57 should be listed here. Why is 57 not here? And how would it be reporting that information if it's not listed? 57 is originated. It's connected. So show IP EIGRP topology, that's where we're going to see that. It's really important, guys, especially with the CCIE lab. The topology is way more complicated than what we're dealing with here. So try to familiarize yourself as much with the topology as possible. And oftentimes you're going to have to go through a couple of iterations to kind of figure out what's going on. I recognize, of course, that 57 is a connected route. I'm curious how it's applying. Doesn't look like 57 is part of the EIGRP process. I wonder if I left that one out. Show IP interface brief. Why it has a metric applied of that. Show run. Yeah, let's do show IP protocols. So it looks like 57 is actually not included. We've got 45, but we don't have 57. Well, that makes sense, actually. We don't really want to run EIGRP on that external link. But it's curious that it's applying that particular metric. Because if I look at the metric for in router 4 to reach router 5, show IP, let's do this. So I'm curious where it's pulling this number from. It's receiving it from the route reflector client, which is router 5. So this must be the metric to reach router 5 then in that particular case. So if I do a show IP route EIGRP, I should probably see that that's the metric to reach 5.5.5.5. Yeah, there we go. Okay, I knew we'd get there eventually. So that kind of goes to what I'm saying, though. It's really important that you kind of can walk through this pretty quickly. If you're running into a situation where you're trying to identify why something is happening or why something is occurring. Usually with the lab, though, it doesn't get into that much detail. They're not going to be asking you to discover or decipher things. They're just going to ask you to configure or fix things. And so if you get them working the way they're supposed to be working, you don't necessarily have to analyze it to this level. But these are the kinds of things that you should look for based on your knowledge. And it makes sense, right? Because we're talking about reaching the next hop in this particular case. If I go up here and I look at essentially who's advertising that particular next hop, this is the next hop value. Who's advertising that? I'm really trying to identify how do I reach that particular peer, okay? And it's still interesting to me because 3.3.3.3 has the same metric as 5.5.5.5. So there's something else kind of going on here, but because if we were following the same logic, then this metric should be the same as this metric, because 5.5.5.5 makes sense. To reach that particular peer is 130.816, but to reach 3.3.3.3 is not 3072. However, to reach the 37 subnet, it is 3072. So BGP is coming up with these numbers somehow. But the idea here, of course, is that we understand why we're choosing the top path based on this path here, which is identified as the best path, as opposed to these other paths in this particular topology. Okay. Remember, this selection list itself. Did I answer your question, Mike, by the way, about the difference between metric and med, at least?
Oh, yep.
All right. So remember that this selection list is processed from the top down. Once a match occurs, we exit out of that particular selection process. So just like an access list or a route map, once I've made a decision, I don't continue to identify other options before I make a decision. So in this particular case, we're choosing the best route based on the lowest metric, which is identified in the database. That means that changing attributes lower than this in the list, like for example, changing the router ID, isn't going to affect anything because we're already making the decision prior to that point. All right. So in general, we always need to know why we're making the decision first in order to know how we're going to influence that decision process. We're making the decision based on, in the case of local preference, for example, then AS path is not going to affect our decision process. If we're changing our decision process based on adjusting the weight, then nothing else is going to matter in the decision tree. Once we make our path selection, we're going to advertise that particular route or that choice to the other peers. All right. So if I go to router 2 as an example, as a route reflector client, well, I'll compare it to router 4 here. That was weird. Show IP BGP. You can see we have lots of choices, right, as far as reaching different destinations. But if I go to router 2 and do a show IP BGP, we don't have a lot of choices. We only have a single choice for each option. This could be a very quick indication that there is some sort of route reflector configured in the topology, right? So it doesn't necessarily mean that, but the point is that we're hiding the topology based on the fact that router 4 is a route reflector client. There's, a route reflector, and then router 2 is a client to router 4. Lots and lots of ways we can see that. All right. If we were to use weight in order to make the selection, how can we use weight in this particular design to influence our process? If you think about weight, it's a non-transitive attribute. It's a proprietary attribute, so it's not well known. And it's not propagated to peers. So rather than choosing the 37 path, if I wanted to say go to router 5, there's really nothing I could do on router 3 or router 5 to change that behavior. I could certainly do something on router 5 to decide whether I'm going to use the bottom link or the top link based on weight, because it's a local decision, but it's not going to influence how router 4 routes. All right. So in the case of having a route reflector, I'll get to your question in a second, Ken. In a case of having a route reflector, we know that this is an easier thing to do because router 4 is the one that's ultimately making the decision. Do I go to router 5 or router 3? And so if I configure the weight on router 4, I can influence that particular decision process. Ken said, why are there so many rib failures, right? These rib failures are not necessarily a bad thing. They just simply represent that we're probably learning about this prefix through a different process. And in our case, it's through the EIGRP process. So all those loopbacks, 1, 3, 4, 5, 7, 8, not 8, that's external, and not 7, that's external, but certainly 1, 3, 4, and 5, as well as the 37 subnet, which is the link between router 3 and router 7. We're not choosing to use those paths because they're being learned through EIGRP. So if I do a show IP EIGRP topology, you'll see all those listed in this topology database. There's the 1, there's the 3, there's the 2, there's the 4, and there's the 37. Which means essentially that I'm not sure why we're putting 37 in there, but I'm going to go ahead and leave it anyway. Because these are being selected through EIGRP, we're using our IGP for reachability rather than BGP. So that's why we see those rib failures. Okay. So router 4 is a route reflector, which means it's making the decision on the behalf of the rest of the network, because route reflectors are used to hide the topology details, if you will, and basically to cut down the load on the control plane. So in this case, we simply change the weight on the route reflector, and we can influence the path selection process. Now there's a couple of things that we can do. We can configure a route map, which is what we're going to do. Or we can apply maybe a weight to appearing relationships and so on. It's just a matter of whether or not you want to do this on a per prefix basis, or do we want to do this overall. All right. If we want to do it overall, then we can just apply that value to a neighbor relationship. But we're actually going to do it for a specific route. Let's just go ahead and do it for the 78 route. So prior to doing this, let's go ahead and identify how show IP BGP 172.16.78.0/24. How router 4 is presently routing to the 78 prefix. It's going to router 3. It's going over that link from 3 to 7, and then it's going across over to the connected route, or the connected link on router 7. All right, so let's go ahead and change this. We're going to go config T, route map, and let's just call it stuff in _R5. And we can do a whole bunch of different match conditions. We can match on local preference, we can match on metric, we can match on the route type, AS path, etc. In our particular case, we're actually going to match on a prefix list. So I guess I should go ahead and create that prefix list first. IP prefix -list. And this is going to, we'll just call it 78, and we're going to permit 172.16.78.0/24. All right. And then we'll go back into our route map, and we're going to do a match IP address. Make sure that you put in prefix list here, because you can put in the name of a list, right? So a lot of people run into this situation. It says word here, meaning that I want you to give me the name. But if you don't put in the keyword prefix list, it's going to assume that you're referencing an access list and not a prefix list. That is something that you could definitely kind of fall victim to on the lab. So we want to make sure we do prefix list, and then we'll simply reference 78. All right, then we can also do a whole lot of set conditions, a lot of options for set. A lot of these happen to have to do with BGP specifically, because we use route maps quite a bit. But there are some that are not specific to BGP. They can be used for other policy-based routing decisions. In this case, though, we're going to set the weight. It doesn't really matter what we set the weight to, as long as it's not 0, because 0 is the default unless it's a locally originated route, and we're talking about an external prefix. All right, so we're going to set the weight to 1. All right, because everything is essentially not weighted by default, we don't care, right? The locally originated routes would be weighted, but nothing else is. So once we're done with this, we need to make sure that we have an explicit permit as well. You don't want to permit 20. You don't want to set up a route map and not have some sort of explicit permit at the end, unless you want to filter everything out. Right? I mean, at the end of every route map is a implicit deny all. All right, just like an access list. So generally, we just end with some sort of generic permit. Okay, so if I do a show route map, do show route map, we can see the route map that we've created. We've got sequence 10 matching on this prefix list with setting the weight to 1. And then we've got our sequence 20, which has no match condition, no set condition, which is basically just like go ahead and do whatever you're normally doing by default. All right. So let's do this before we clear our BGP process. Let's do a show IP BGP 172.16.78.0/24. And we don't see, we're still using router 3. This is the best path. Remember, these attributes don't get applied until you finish or until you've completed a refresh between the peers. All right. Now we could do a clear IP BGP star N, do a soft reset on all of our inbound policies, but let's go ahead and just apply this to router 5, because essentially that's what I'm trying to do. I'm trying to apply this weight to the routes that I'm learning from that particular peer. Except we haven't done one thing yet. We need to apply this in the BGP process. So router BGP 100, neighbor 5.5.5.5, route map, and this guy right here, SUF. I guess I misspelled it. It's supposed to be called stuff, but that's all right. Okay. So again, let me get out of this exit, go back to the prefix, we still haven't affected the path, even though we've applied this to the peering relationship. We haven't affected our decision process. So let's clear, do a clear IP BGP 5.5.5.5 in. Okay. And now if I look at the prefix, I should see that it is now choosing to go through router 5, and I can see the weight applied to the prefixes from that peer. All right. So my path selection now is 50 through 57. If I do a trace to 172.16.78.8, I source that from loopback 0. I can see that I'm going over the 45 link between router 5 and 7, and then finally over to 78.8. So it's a pretty simple process, right? You create a route map, you match your conditions, and then based on those match conditions, you set the different attributes. The only problem with BGP, and this is where you probably run into the situation on the test, is that unless you're completely familiar with the decision tree, the algorithm, if you will, to select the path, unless you're vastly familiar with that and you understand what they're trying to ask you with regard to how to manipulate things, it can be a little bit challenging trying to figure out how you can do something, because there's lots of ways we could accomplish essentially the same goal. And there are also side effects of what we're trying to do here based on other things or other factors that might happen in the topology that could affect this decision process. All right, now this should be reflected on the other routers. Router 2 previously for the 172.78 network was going to router, the next hop attribute was 37.7. So I should see that that has changed now for that particular prefix to 57.7. So router 4 has selected a path based on the condition that we applied, applying the weight with the route map. That's what ended up being advertised to the route reflector clients. So we effectively changed the behavior of how everybody routes to that destination. So like I said, it's really important to understand the path selection. Why is it one path versus the other? Not only do you have to understand the attribute list, right? How do you process it top down, but you need to understand the individual peering structures as well. In this exact topology, we can change the behavior of routing based on who we're peering with. So changing the weight on one router that isn't a route reflector, for example, if I change the weight on router 2 or router 3, it wouldn't have any effect on a routing decision overall. All right. This is why local preference is actually useful, because changing the local preference affects everybody in the network or in the autonomous system. All right, so let's take a look at local preference. The highest local preference should be preferred. First of all, you guys have any questions about weight? It's a pretty simple, straightforward process. I just want to make sure before we move on to local preference that you don't have any questions about weight. Okay. If you do, send me something in the chat window there. So let's talk about local preference. The highest local preference should be preferred. Let's say, in this case, we're going to do something a little bit different here because I want you to see how this works as well. Let's say based on this particular topology, we want all the routes in AS50. We only have one technically, 8.8.8.8, to go through router 5 no matter how we learn them. So router 1 I want to send over to router 5, even though it's a longer AS path. To go to router 5 and then go to router 7, go to router 8. Let's take a look at how we're routing to 8.8.8.8 from router 1's perspective right now. There we go. Show IP BGP 8.8.8.8/32. So it looks like we are learning about both paths. We're learning about it from a route reflector, and we're learning about it directly from router 8. Now in this case, AS path was longer here. Metric was the same. Local preference is the same. But are we choosing this based on internal versus external or AS path, right? Well, if we go back to the list, we can see that AS path is after, actually before, excuse me, is before the decision of whether it's internal or external, okay? Because, well, locally originated, again, does not reference origin, or whether it's a internal versus external path. And actually, if I look at this, it isn't until I get to step 7 that I decide whether I'm going to choose between internal and external. So in this case, we're deciding primarily based on AS path. Does that mean that if we change local preference, we should be able to influence that? And the answer is yes, because local preference is the second choice in the list. Okay? So we should be able to influence that decision. So based on this topology, I want any routes originating on AS50, and we only have one path in this one route in this path. There's another way I could see that, by the way. I could just go to router 4 and I could say show IP BGP regx, and we'll say $50 sign, right? So we can see there's actually 3 different paths that are originating from this autonomous system. We've got route 8.8.8.8, 172.16.18, and 172.16.78. Okay, and it looks like router 4 is pretty much making the same decision, with the exception of 8.8.8.8 to reach those destinations. It's going directly to the external peer for 18 and 78, but it's actually going to router 3 for the 8.8.8.8 prefix, which is kind of interesting if we think about that. Let's do that. Let's take a look at that. Show IP BGP 8.8.8.8/32. So why are we choosing that particular path? It has to come down to, well, actually it's interesting because, this is why, right? Normally it would be choosing this particular path here, but because the next hop is not we can't recurse to the next hop, we're not using that particular path. And that's because that 18.8 prefix is not being sent into BGP, or that 18.8 next hop. So if we did a next hop self on router 1, then that would end up being the path that was chosen because we changed that next hop value for that particular destination. All right, but we're going to leave it. It doesn't really matter. We're going to just see how we can influence this decision process based on the use of local preference, applying it using an AS path access list as opposed to a prefix list and other conditions. All right. Without really looking at the details, we can kind of see how a path is selected. For example, we can see the local preference is the default value, the metric is the default value, the weight is the default value. So we would assume that AS path would be the best choice, but again, it has to do with reachability. If I do a show IP route, show IP Ceph, excuse me, of 172.16.18.8, I've got a recursive loop. That's the reason why it's not being implemented. I don't want to take a lot of time trying to fix that. We've been making a lot of changes here. So we probably introduced that by redistributing a redistributed route, but that's okay. We don't really care about that. All right. All I want to show you guys is how we can influence this decision, and then we'll wrap it up. Okay. So if I did a trace to 8.8.8.8, I know how it's gonna get there. All right. In fact, let's do that. Trace route 8.8.8.8 source loopback 0. All right. So we're going to router 3. Then we're going to router 7, and then finally over to router 8. Not the best path, but we're definitely going to router 3. So I want to influence this and say, hey, let's go ahead and change that so that we choose router 5. All right. Again, there's lots and lots of ways you can do this, I mean, we are still going through AS51, but we're not choosing to go through router 5. So we're going to make the changes on router 5, but we're going to make it implicit for all of the AS50 routes, not for specific prefixes in this case. So in this case, what we're going to use is an IP AS path access list. Okay. You could match the prefix, but we're not doing that. We're not matching based on a specific route or any other match attribute. We're simply going to match based on the AS path numbers, and then we categorize it based on that. And this is really where understanding and knowing how regular expressions work really helps out a lot, because it is possible you might be required to do something like this in the lab. So we're going to do an IP AS path access list 1, and we're going to say permit $_50, right? Indicating that we're matching on paths that originate from AS50. All right, so let's go ahead and create a route map. This time I'll call it right stuff in from R7. Permit 10, and we're going to match IP address. Now in this case, we're matching not IP address, excuse me, AS path. And we have to reference the AS path access list that we created. If I did match IP address, I'd be trying to match a prefix. All right, and we're just simply going to do a set local preference to 200, and then make sure we put in our implicit or explicit permit all at the end. All right, now I would apply this to the peer. But before we do that, let's do a show IP BGP. BGP for 8.8.8.8/32. And we can see that the local preference is 100, 100, 100 for that particular destination. And we've decided to take this path. So router 5 is using 57.7. If I go to router 4 and I do a show IP BGP, notice that it hasn't changed. We're still going to router 3. So again, I need to apply this to the neighbor first, and then I need to clear the relationship that I have with that particular peer. I'm actually going to only apply this on the 75 link. We actually have two different links here. We've got 75 and we've got 57. I could apply it to both, saying anything that comes in from 57, anything that comes in from 75. And I would probably want to do that and then maybe use a different method for matching which egress interface I'm going to use to get over to router 7, where wait could come in, or some other AS path prepending, or even a med that's coming from router 7 would allow me to choose which external link to use. But doesn't really matter. We're going to apply it to the 75 link, okay, or the peer on the 75 link. So go back to router 5, router BGP 100. And we're going to say neighbor 172.16.75.7 and route map and this guy right here in. All right. Oops. Helps if I put a period there. And I'll do a clear IP BGP 475.7 in. All right. So now if I go back to router 4, I should see only one decision. Right. And that makes sense, because I'm getting a local preference of 200. Router 4 says, you know what? Well, router 5, first of all, is only advertising that decision. And router 4 is essentially trusting that decision, and it's receiving that from that particular peer. All right. It's interesting that this metric changed to 3072, though. I believe that was a different value before. Yeah, right here. So there's something going on with that value, that calculation. I'd have to do a little bit more investigation as to how it's being calculated, because it likely shouldn't have changed, but it's definitely how we're making the decision in the tiebreaker that we were talking about at the beginning of the lesson. All right. Because we have a local preference, we don't see the alternate path. We only advertise the path, which is a loop prevention mechanism in our BGP topology. So the path with the highest local preference is now the path of choice. Even if I go over to router 3, show IP BGP 8.8.8/32, you can see in this case the best path is to the route reflector, but it's still coming from that link from 75.7. Okay. And this is interesting because we're actually choosing an internal path as opposed to an external path, which is normally not the case, but we're overriding that behavior. We can see the local preference is set to 200. All right. So this is an example of grouping the prefixes based on their AS path information, because it's a general attribute that belongs to all of the routes, as to opposed to matching prefixes individually. It depends on the question on the exam that's posed to you. On the exam, if they're not specific, you could simply accomplish the goal by doing something more generic. All right. So, for example, they might be looking for the result, show IP BGP as opposed to the configuration. All right. All right, guys, that's weight and local preference. We will take a look at, in our next lesson, AS path and multi-exit discriminator, and we'll talk about how we can use those attributes to affect our routing decisions as well. All right. I will send a Slack message to identify when we're going to probably do that lesson. It's probably going to be... I'm thinking either tomorrow or Thursday. I'm going to send out a message and we'll get it coordinated. All right, so we'll wrap up this lesson. We'll see you guys in the next lesson.